We have so far discussed the properties of U statistics based on observations from a single population. We have discussed small sample and large sample properties. But there may be more than one population in practice. So, in this module, we shall explain the concept of U statistics and enumerate the properties with several examples when observations are available from two populations. We have discussed so far properties of U statistic based on observations from a single population. That is, we have mentioned small sample properties like unbiasedness and minimum variance. Among large sample properties, we have discussed consistency and asymptotic normality of U statistic. We have also discussed degeneracy of U statistics. All these discussions are supported by a number of examples. But in practice, observations can come from several populations. In this module, we shall discuss the formulation of U statistic and enumerate associated properties for observations from multiple populations. Assume that we have observations from two independent populations. We start with the concept of a functional. Suppose x1, x2, xn are IID observations from F and y1, y2, ym are IID observations from G. Assume that the two samples are independent. F and G are unknown but known to be continuous. Suppose script f is a class of all absolutely continuous distribution functions. Then a functional theta fg is a real valued function defined on the Cartesian product space of script f and script f. For further discussion, we suppress the arguments f and g and call the functional simply as theta. Now, consider the estimability of a functional. Theta is said to be estimable if there exists some estimator which unbiasedly estimates theta. That is, formally, theta is said to be estimable if there exists a function phi with arguments x1, x2 up to xa and y1, y2 up to yb such that expected value of phi equals theta for every fg belonging to the product space. Then phi is called a kernel for estimation of theta. Minimum value of the pair AB with AB both less than equal to small n, ensuring the above, is called the degree of the kernel. Now, what is a symmetric kernel? In single sample situation, permutation invariance of phi indicates symmetry of phi. But now we have arguments from both the populations. So, consider a kernel phi with arguments xi1, xi2 up to xia from the first population and yj1, yj2, yjb from the second population. Then phi is said to be symmetric if it remains unchanged for separate permutations of i1, i2, ia and j1, j2, jb. As in the single sample case, corresponding to any asymmetric kernel, we can always find a symmetric kernel. The idea is, as before, to take the average of all possible phi values as the new kernel, and the average will be a symmetric kernel for this situation. Now, we shall explain symmetry and kernels through some examples. For all these examples, assume that in IID observations are available from capital F and small m IID observations are available from G, and these two samples are independent. Now look at example 1, that is estimation of the functional theta equal to probability x1 less than y1. Since probability x1 less than y1 is nothing but the expected value of the indicator function of the event x1 less than y1, we take the kernel as indicator x1 less than y1, then phi is a kernel of degree 1, 1. Of course, the symmetry is immediate. Next, look at example 2, where the objective is to estimate the joint probability of x1 less than y1 and x2 less than y1. As before, since the expected value of theta equals the indicator of x1 less than y1 and x2 less than y1, the kernel is the indicator function of x1 less than y1 and x2 less than y1. Then phi takes two x's and one y as the arguments. Thus, phi has degree 2, 1. Now, consider a different permutation of x1, x2, that is x2, x1. Observe that phi remains the same if we consider x2, x1 instead of x1, x2. Thus, by definition, phi is a symmetric kernel. Next, consider example 3. Consider estimation of probability x1 less than y1 less than x2. As before, since expectation of the indicator function is a probability itself, we take the kernel as indicator x1 less than y1 less than x2, then phi is of degree 2, 1. But phi is not symmetric. This can be seen if we interchange x1 and x2. Consider kernels corresponding to different permutations of x1, x2. We find that the corresponding symmetric kernel is the average of indicator x1 less than y1 less than x2 and indicator x2 less than y1 less than x1. Next, consider estimation of the difference of variances. That is, theta equals variance of x1 minus variance of y1. It can be remembered that for variance of x1, the kernel was x1 square minus x1 x2, and that for variance of y1 was y1 square minus y1 y2. Then we take the kernel for theta as their differences. That is, we take x1 square minus x1 x2 minus within bracket y1 square minus y1 y2. But such a kernel is asymmetric, and as earlier we set the symmetric kernel as half x1 minus x2 square minus half y1 minus y2 square. Clearly, the degree of the kernel is 2, 2. Now, we come to the definition of a U statistic in two samples. First of all, we define C1, the set of integers I1, I2, Ia such that 1 less than equal to I1 less than I2 less than up to Ia less than equal to small n, and define C2 as the set of J1, J2, Jb such that 1 less than equal to J1 less than J2 up to Jb less than equal to small m. Then we have in total n choose A into m choose B possible kernels of degree AB. Now come to the definition of a U statistic. If phi is a symmetric kernel of degree AB, then the corresponding U statistic is defined as double sum over C1, C2, phi with arguments xi1, xi2, xia and yj1, yj2, yjb, whole thing divided by n choose A into m choose B. Now, we quickly state the small sample properties of the U statistic. As earlier, U is unbiased. Since U is symmetric in its arguments, it can be expressed in terms of the full set of order statistics. Therefore, U is based on the complete sufficient statistics. Thus, U is minimum variance unbiased estimate of theta even in two samples. Now, we shall derive the exact variance of U statistic. As in the single sample case, the different terms of U are not all uncorrelated, and hence we need to consider the contributions of the covariance terms in the expression of variance of U. First of all, assume that C and D are such that C plus D greater than equal to 1. Now, define phi CD with arguments x1, x2 up to xc and y1, y2, yd as expected value of phi x1, x2, xa, y1, y2, yb given xi equal to small xi for I from 1 to c and capital Yj equal to small yj for j equal to 1 to d. Naturally, the suffix of phi represents the number of x and y variables which are held fixed. Also define sigma square cd equal to covariance between phi with arguments x1, x2, xc, xc plus 1 up to xa and y1, y2, yd, yd plus 1 up to yb, and phi with arguments x1, x2, xc, then x dash c plus 1 up to x dash a, and then y1, y2, yd, and y dash d plus 1 up to y dash b, where xi dash are iid as f and yj dash are iid as g. Then the exact variance of u can be expressed as variance of u equal to summation over all possible c and d such that c plus d greater than equal to 1, a choose c into n minus a choose a minus c divided by n choose a into b choose d into m minus b choose b minus d divided by m choose b into sigma square cd. We refer the readers to the book by Webding for details of this variance derivation. Next, we concentrate on finding the exact variance of some U statistic. Consider in example 1, where the objective is to estimate the difference of the means. Naturally, the kernel is x1 minus y1, which is symmetric and of degree 1, 1. The corresponding U statistic is simply x bar minus y bar, that is, the usual estimator of the difference of sample means. Since phi has degree 1, 1, we have the choices 0, 1, 1, 0 and 1, 1 for CD. Thus, for the calculation of variance, we need to calculate sigma square 0, 1, sigma square 1, 0 and sigma square 1, 1. Now, by definition, sigma square 0, 1 is a covariance between phi x1 y1 and phi x1 dash y1, where x1 and x1 dash are two independent copies from F. Thus, we get sigma square 0, 1 as the covariance between x1 minus y1 and x1 dash minus y1. Since x1 and x1 dash are IID, they are uncorrelated, and y1 and x1 dash are uncorrelated, we get the covariance as variance of y1. Similarly, we get sigma square 1, 0 as variance of x1 and sigma square 1, 1 as variance of x1 plus variance of y1. Then, a simple manipulation expresses the variance as variance of u equal to variance of x1 by small n plus variance of y1 by small m, which is the usual variance of x bar minus y bar. In our next example, that is in example 2, we consider the estimation of probability x1 less than y1. Naturally, the kernel is the indicator of the event x1 less than y1. Thus, phi is nothing but the indicator of x1 less than y1 and phi is symmetric with degree 1, 1. The corresponding u statistics is simply the proportion of observations such that xi less than yj. Then, this u is the famous Mann-Whitney statistic for comparing distributions. As earlier, we have the choices 0, 1, 1, 0 and 1, 1 for C, D. Thus, for the calculation of variance, we need to calculate only sigma square 0, 1, sigma square 1, 0 and sigma square 1, 1. Note that sigma square 1, 0 is nothing but the probability of x1 less than y1 and x1 less than y1 dash minus theta square, since expected value of phi is theta. Now, we observe that y1 and y1 dash are IID. Then, we conditionally fix x1 so that probability x1 less than y1 and x1 less than y1 dash becomes the double expected value of indicator x1 less than y1, x1 less than y1 dash, where x1 is conditionally fixed. Now, the inner expectation is with respect to the conditional distribution of y1 and y1 dash. Since x1 is independent of y1 and y1 dash, the inner expectation reduces to 1 minus g of x1 whole square. Thus, we finally get that probability x1 less than y1 intersection x1 less than y1 dash equals expected value of 1 minus gx1 whole square, where the expectation is taken with respect to the distribution of x1. Similarly, we find sigma square 0, 1 as expected value of f square y1 minus theta square. Since indicator of x1 less than y1 has a Bernoulli distribution with parameter theta, we get sigma square 1, 1 as theta into 1 minus theta. Combining all this, the final expression follows. In our next example, we consider estimation of variance of x1 minus variance of y1. The kernel is x1 minus x2 square minus y1 minus y2 square, whole thing divided by 2. Naturally, the corresponding u statistic simplifies to s square x minus s square y, where s square x is the sample variance with divisor n minus 1. Now, phi has degree 2, 2, and we have a total of 3 square minus 1, that is 8 possible choices, namely 0, 1, 1, 0, 1, 1, 1, 2, 2, 1, 2, 0, 0, 2 and 2, 2 for CD. Considering a simple use of conditioning technique, we get sigma square 0, 1 equals variance of y2 minus mu y whole square and sigma square 1, 0 equals variance of x1 minus mu x whole square. The remaining expressions are also straightforward to derive and hence we skip the details. But looking at the expression of u, the u statistic, we suggest a simple alternative. U is actually a difference of two univariate u statistics. Again, the two univariate u statistics are independent. That is, we can write u as u1 minus u2, where u1 and u2 are independent univariate u statistics. Then, variance of u naturally equals variance of u1 plus variance of u2. Considering examples on single sample u statistic, the variances of u1 and u2 and hence the final expression of variance of u can be obtained. Now, consider large sample properties of u, that is consistency. However, we provide only assumptions and the results but skip the details. Let u be the u statistic corresponding to a symmetric kernel of degree AB. Denote the total sample size by capital N equal to small m plus small n. Assume A1 sigma square CD greater than 0 for CD equal to 0, 1, 1, 0 and AA. Suppose for each capital N equal to small n plus m, there exists subsequences small n and small m such that as capital N tends to infinity, minimum of small n tends to infinity and small n by capital N tends to lambda and small m by capital N tends to 1 minus lambda, where lambda lies in the open interval 0 to 1. Naturally, lambda equals to 0 or lambda equals to 1 gives a degenerate case. Then, under conditions A1 and A2, n times variance of u tends to sigma square, where sigma square equals a square sigma square 1 0 divided by lambda plus b square sigma square 0 1 divided by 1 minus lambda. Now, we come to the consistency. We have expected value of u as theta. Then, from the representation, variance of u equal to 1 by n into n times variance of u, we find that as minimum of mn tends to infinity, n times variance of u tends to sigma square, but 1 by capital N tends to 0. Combining these, we get variance of u tends to 0 and hence the consistency follows. Next, we shall consider asymptotic distribution of u. However, we provide only the outline of the proof. Under conditions A1 and A2 above, as n tends to infinity, then the limiting distribution of square root of n u minus theta is normal 0 sigma square, where sigma square is as specified earlier. Now, we shall give the outline of the proof. Define Zn as square root of n into u minus theta minus a into square root of n by small n summation phi 10 xi minus theta minus b into square root of n by small m into summation j from 1 to m phi 01 yj minus theta, where phi 10 and phi 01 are already defined. Then it is natural to see that expected value of Zn is 0 and summation I from 1 to n phi 10 xi minus theta whole thing divided by small n is the average of IID random variables. Therefore, by CLT, the second and third terms in the right hand side of Zn are independent and asymptotically normal. Moreover, expected value of Zn square tends to 0 as n tends to infinity. Thus, Zn converges in probability to 0 as n tends to infinity. Therefore, square root of n u minus theta and a into square root of n by small n summation phi 10 xi minus theta plus b into square root of n by small n summation j from 1 to m phi 01 yj minus theta have the same asymptotic distribution. The latter is asymptotically normal 0 sigma square and hence the proof is complete. Now, note that phi 10 xi and phi 01 yj are independent. Therefore, these terms are independent. Now, let us consider some examples. Consider example 1 again, where the u statistic is x bar minus y bar. Now, applying the above result as n tends to infinity, we have the limiting distribution of square root of n x bar minus y bar minus theta is normal with mean 0 and variance sigma square, where sigma square is nothing but sigma square 10 by lambda plus sigma square 01 by 1 minus lambda. Now, we have already defined or rather derived that sigma square 10 equals variance of x1 and sigma square 01 equals variance of y1. Thus, we get the asymptotic variance as variance of x1 by lambda plus variance of y1 by 1 minus lambda. Thus, we just note that for the asymptotic distribution, we need only to derive sigma square 01 and sigma square 10. Next, consider example 2 again. Here, the u statistic is a proportion of observations such that xi less than yj. Then, as earlier, the asymptotic distribution of square root of n into u minus theta is normal 0 sigma square, where sigma square is sigma square 10 by lambda plus sigma square 01 by 1 minus lambda. Naturally, sigma square 10 takes the form integral 1 minus capital Gx whole square dfx minus theta square, and sigma square 01 takes the form integral fx square dgx minus theta square. However, if we assume f equal to g, that is for testing equality of distributions we often assume f equal to g, then under f equal to g we have theta equal to half, because under f equal to g x and y are IID, therefore probability x less than y is nothing but half, and a simple calculation gives sigma square 10 and sigma square 01 as 1 by 12. Thus, under f equal to g, the distribution reduces to square root of n u minus half converges in distribution to normal 0, 1 by 12 into lambda into 1 minus lambda. Now consider example 3 again, that is estimation of the difference of two variances. Then with the already derived expressions as n tends to infinity, square root of n multiplied by u minus theta converges in distribution to normal 0 sigma square, where sigma square is nothing but sigma square 1 0 by lambda plus sigma square 0 1 by 1 minus lambda. Now sigma square 1 0 is already derived as variance of x1 minus mu x whole square, and sigma square 0 1 is derived as variance of y2 minus mu y whole square. Therefore, it is easy to observe that the asymptotic variance, that is sigma square, is a weighted sum of the asymptotic variance of two univariate U statistics, and the weights are inversely proportional to lambda and 1 minus lambda respectively. We have thus defined the two sample U statistics, that is when samples from two populations are available. We have discussed different properties of a two sample U statistic like unbiasedness, minimum variance, consistency, and asymptotic normality. In our next module, we shall explain the notions of hypothesis testing and confidence interval estimation in the context of non-parametric inference.